Chapter 7. Also specification. If you recall from our last episode, Chapter 6 was specification, choosing the independent variables. This is now specification, choosing a functional form. And this means, roughly speaking, let's say you're estimating a demand curve. It could be shaped like that, or like that, or I guess less likely, but like that. Actually, that looks more like a production possibility frontier. So, just because it's negative doesn't mean it has to be a straight line. So this is going to be a little bit about that, about choosing what form you want to put the variables in. And this has some really important applications. Having said that, I kind of treat this chapter as kind of a menu book. I don't ask the class to remember a lot of details from this chapter, other than this is the place you go if you're thinking about functional form. And it covers a little bit more than just functional form in here. Indeed, the first thing he talks about, which is related to functional form, but that is never suppress the intercept. How do you do that? Well, y sub I is equal to beta sub 0 plus beta sub 1 x sub I. How would you suppress the intercept? You can do this instead if you want to. You can estimate it without an intercept. And technically there is an intercept, it's just the intercept is 0. This is not a good idea for several reasons to do the second one. Sometimes there's an economic concept where you're required to do that, but it is extremely rare, and you would know from the background theory and from doing the literature review that you should do this. And even then, it's not as reliable, but the theory itself may require you to do that. I think I've done that at least once in some sort of exchange rate paper. I don't remember now. And here's why. A couple of reasons. One is, why on earth would you simply assume that the intercept is, because in a sense you're not suppressing the intercept, you're requiring the intercept to be 0. What if this is the actual relationship? But then you have those same data points and you tell the computer you must start here though. Oh, I'm sorry, I probably should have drawn a little bit further down to the right. But you're going to get something like that, right? And the slope is way off. You're biasing the slope something awful by requiring the intercept to be 0. The other problem is that was raised in an earlier chapter was that the intercept can take into account the problem that's created when the mean of the stochastic error term is not 0. Now, there ain't nothing you can do about figuring that out, but you don't have to. The computer automatically adjusts for this. The computer automatically fixes a potential problem with the stochastic error term if you allow it to include the intercept. If you allow it, I shouldn't say, because I don't like it, I know that's the way it's worded. It says, suppress the intercept. Well, you're not suppressing it. You're just requiring that it be 0. If you don't require that it be 0 and you let the computer estimate it, you have automatically solved a couple of serious problems with your data that if they don't exist, it doesn't have to solve it, but if they do exist, it does it for you automatically. So always, unless the theory suggests otherwise, make the computer estimate an intercept. But wait, there's more. Well, what was I just about to tell you? Oh, yeah. However, that also means that you should not bother to place much faith in the estimate for beta sub 0, because there are a number of things that can cause it to be off base, all right? For example, I'll beat the hours grade thing to death here. Grade equals 15 plus 3 times hours. All right, we'll make this our estimated regression equation. Sub I. All right. It sure would be nice if we could think to ourselves, for every 1 hour of study, a student makes 3 points higher, plus 15. I described in an earlier video this intercept being like what you would get if you didn't study at all. And that's a good place to start. But really and truly, once you understand the background material, it's not really true. You can't put much faith in this estimate right here. You must allow the computer to do it. But you can't think to yourself, oh, that's what we would get if they didn't study at all. No, that's a number that was generated that could represent that if there were no other problems with the data. But if there were problems with the data and the underlying relationship, then this could be biased well away from what the intercept should be. Long story short, you don't trust the intercept. And notice, in the last video I showed you a number of times my regression results from a paper that is out under review right now. You notice what I don't even have on there? I don't have the intercept on there. I never bothered to show the intercept. All I showed were the parameter estimates for each of the independent variables and the t-scores. All right, I did not bother to show the intercept, and I never do. I mean, and this is very common. So because we must include it, but you can't rely on it. All right, so that's the first big lesson of Chapter 7. The second one is all about alternative functional forms, which is what I was showing you earlier with the curved lines and so forth. And remember the awake variable? I told you I was going to bring that back up again. The awake variable, I said, represented the number of consecutive hours the student had been awake. And the idea was to try to capture the effect of the negative impact of people pulling all-nighters, all right? And as I explained in the last video, of people pulling 3-dayers, as I did when I was trying to catch up on the reading in Soviet foreign policy class. And let's say these are, to make it a little bit more realistic, consecutive hours beyond 8. Or let's say 16 hours a day, you sleep for 8 hours, you stay awake for 16, beyond 16, all right? So this is consecutive hours you've stayed awake beyond 16. Now notice here that by measuring it this way, we are assuming that the additional negative effect from staying awake for 2 extra hours of beyond 16 is exactly the same. The additional negative impact is exactly the same up here as it is down here. And maybe physiologically that's true. Maybe that's right. But what if medical science tells us that actually the more tired you are, the more that extra hour is really going to add significantly to your lack of ability to sort of rationally figure out answers to questions and form sentences and so forth? What if this increases exponentially? Well, then what you could do is, rather than measure this variable as awake, it could be awake squared. So check this out. Awake squared is 1, 4, 9, 16, 25, 36. And now notice, the increased exhaustion from staying up from 1 hour to 2 hours is a factor of 3, whatever this exactly represents, whereas down here, it's plus 11. All right, so the impact of staying awake for an extra hour when you've already been awake for 16 plus 5 is different than the impact of an extra hour when you've been awake for 16 plus 1. And maybe that's the way it really works. And this would be a way you could capture that. You could square that variable. And that's the way it would affect the regression analysis. So, a really handy thing that you can do. I've actually used this. In a study I did of exchange rates, one of the variables I wanted to include was something called cash in, the cash in effect. And I think you'll find this pretty intuitive here. Cash in effect. 1, 2, 3, 4, 5, 6. Okay, so I was reading this study about exchange rates by a guy named Stefan Schulmeister, and he was referencing what he called the cash-in effect, which is also very common in the stock market. In the stock market or in the currency market, if there is a sustained appreciation of a currency or a sustained appreciation of a financial asset, it tends not to do that over the course of let's say that's the course of a month, all right? A month-long appreciation. Rather, it tends to do something like this. And here is, and you could think to yourself, well, there were some random pieces of news that were negative about the stock or about the currency that was pulling it down. But the theory that he put forward was that, and he's certainly not alone in this, was that what's really going on is, I don't know if you've ever heard this about the stock market, people were profit taking. That when a stock has been appreciating for several days that you're holding, how much money have you actually made? Nothing. Not until you sell it. So the longer a stock appreciates, the greater the anxiety you feel about, if I don't sell it now, I might not make this money. All right? So it's the anxiety you feel over holding an appreciating asset. The longer you hold on and don't cash out, the greater the chance you could lose those paper profits. So cash in, Schulmeister says, is the effect of these consecutive days of appreciation leading people to have this anxiety that causes them, we're going to profit take today. Now, it doesn't mean everybody in the market. When it goes down, all the underlying reasons for the original appreciation are still there, so it goes back up again. Down, up, down, up. And he puts together some very convincing data on how this works over time, and I wanted to include it in my regression model that was showing the determination of exchange rates, the dollar Deutschmark, which doesn't exist anymore, the dollar yen, and so on. But this was my thinking. The additional anxiety that you feel when a currency appreciates from 1 day to 2 days is not equivalent to 5 days to 6 days. Now, down here, man, it's been going up for 5 straight days. It's going up for 1 day, whatever. Going up for 2 days, whatever. But 5 straight days, now you're getting antsy. And so I was hypothesizing that the additional anxiety that you feel from 5 days to 6 days is not equivalent to that you feel from 1 day to 2 days. And so I squared it. One, 4, 9, 16, 25, 36. Plus 3. Plus 11. It worked extremely well. Right? I was very pleased. I showed, consistent with what we just said in the previous chapter, I showed a regression that included it just like this and one just like this, because I could justify either one theoretically. And both of them were statistically significant, because remember, that's the second cutoff. Let me go back to that. The first was theory, the second was the t-score, the third was the adjusted r-square, and the fourth was the possible bias on the coefficients when you removed and added the variable. And so theoretically I could justify either one. T-scores were both really good. So I just showed both results. I was like, I think the t-score was better on this, right? It was better on this. Although Studemans is very careful about this. He's like, look, econometrics is not a perfect tool. You can't really put a lot of significance on the idea that this variable had a higher t-score than this one. That's a very dangerous thing to do. I think there's something to that, but don't get carried away. So yes, this had a higher t-score than this. Did that lead me to conclude this is right and this is wrong, or this has more support than this one does? Marginally, but not enough to say, to relegate this to a footnote. I should still report it somewhere. It's relegated to a footnote. So I included them both, but it did work better this way, all right? And I think you can see the underlying logic here, that in both instances, that it would make more sense to square the variable. Don't use x, which is the number of consecutive days of appreciation. Use x squared. Not y equals beta sub 0 plus beta sub 1 x Don't estimate that, estimate this. Oh, let me write in a different color. Okay, green. Y sub I equals beta sub 0 plus beta sub 1 x sub I squared. Estimate that instead, all right? And do I include that here or later? There's a way to do this in Stata, and it's a generate statement to generate a new variable. If you type in the window down the bottom, generate x sq or something like that equal to x, and I don't remember what the symbol is in Stata for squaring something, to raising it to a power. Some programs is a little hat like that. Some of them it's a 2 multiplication, 2 asterisks to raise it to a power. But what this would do is, if you would name the original variable x, it would go through and create a new variable called xsq that is really the original variable squared. And I think, I have to look back, I think you only have to type GENR actually, rather than generate. But anyway, so that's what you can do to your data, and then run the regression with xsq instead of x. Okay, so that's the basic idea in this chapter, is that you cannot assume that just measuring it as x, or even just as y, there may be reasons to square y, is the way you should do it. Now there are 1, 2, 3, 4, he gives 4 choices in this chapter of ways to measure variables, and I never spend a lot of time on this just because, as I say, I feel like it's one where he has a wonderful summary at the end that we're going to get to. Let me jump to that first, actually. Let me jump to that so you can see where we're headed. There's a carpet right here, which is why when I get to here, a little wheelie chair, and then this thing is a fantastic microphone, but it's wired, and so I end up rolling over top of the wire. Okay. This is what comes at the end of the chapter. Table 7.1, and he goes through and he says, it's a summary of each of the possible forms, which is really fantastic. Okay, so we're going to get to that eventually. First, this is what we've been doing, the linear form. And in the linear form, b sub k, or the beta, the coefficient, is really just the change in y over the change in x. Right? That in this first regression up here, what is beta sub 1? It's the change in this divided by the change in that, or the slope. It's the slope coefficient, all right? So that's been our default so far. What could you do instead? You could take the there we go. We could take the natural log of both sides. We could do this. And once again, you use a generate statement. I don't remember what the generate statement is to create natural log, but there's a help function where you can look that up. And actually, in the Stata help file, which I would have told you about in another video, you can go chapter by chapter. So I haven't looked, but I'm virtually certain that in chapter 7, help file for Stata, that's where it's going to show you how to generate a natural log. But at any rate, take the natural log of y, and the natural log of x. So now, beta sub 1 is equal to, now before it was the change in y over the change in x, right? That was the slope. Well, now it's the change in the natural log of y divided by the change in the natural log of x, okay? So it's just the exact same thing we had before, except instead of change in y over change in x, you put the natural log symbol in front. Now, what difference does this make? Well, how does this help us? Well, it turns out, and this is a calculation that I can go through, and I usually do in the live version of this class, but I also kind of assume that people are going to forget it as soon as I get done. And I don't really want you to remember the mathematics so much as the fact that such an option exists. Because there's a reason why the exams in this class are all open book. When I do stuff like this, I use the book. Not necessarily this book, but I use the book, all right? So I want you to be aware that certain options exist. And you can say, you know, I wonder what functional form I should use for this. Let me pick up an old Studeman book and look at chapter 7. That's what I want you to be able to do. And I want you to have a gut feeling for a lot of the other concepts so that you know what to look for. So likewise here, I'm not going to go through all the math, but what I do want to show you is that this ends up being very similar to the elasticity of y with respect to x. So this could be like quantity demanded and price. Now you've got price elasticity, all right? Rather than having the percentage change for a 1% change in this variable, how much does this variable change over here? You end up with, again, I can go through the mathematics, but it's not really complicated, but it is a little, I don't care if you remember it or not, right? But what you end up with for a 1% change in this variable, if, let's say that the estimate of beta sub 1 ends up being 5, all right? Depending on the units we're using here, then for a 1% increase in this, this goes up by 5. For a 1% decrease in this, this goes down by 5, or it could be, if it's price elasticity, probably -5. So that's really handy. You can do double log form. I've done that before. I don't remember what the context was. But you do the double log form, and then you can have elasticities as your parameter estimates rather than slope coefficients, just purely slope coefficients, and that's really neat. All right. Now, you can do a semi-log form. Yeah, you can do log on one side, but not log on the other. This is double log. Here's semi-log. I didn't do log of this one, but I did log of that one. Or I can do this. I did do the natural log of this one, but not the natural log of x. And what does that give me? Let me show you. Oh, actually, let me back up for a second and show you what the possibilities are with the shape of the function. Over the carpet again. With the shape of the functions. This is all in the book. Again, very good reference. On figure 7.2, it gives you a variety of, hey, if your estimate is so-and-so, then your relationship looks like this. And notice on that first graph there on the right that looks a lot like a demand curve with that constant elasticity demand curve. If you remember, the demand curve that has constant slope doesn't have constant elasticity, but the demand curve that has constant elasticity doesn't have constant slope. So this one would be one where you have constant elasticity but not constant slope, and then a variety of other possibilities over there on the right that, again, I'm not going to go through all this because it can be very tedious, and it may well never come up. And if it does come up, it's going to be in the relevant literature. Okay, semi-log form gives you something that looks more like this, all right? And again, he goes through if you get such and such a variable, such as a parameter estimate will look like this, and so on, right? Then the last one is polynomial form, which is more like what I was doing with the exchange rate stuff. With the polynomial form, you've got a y on the right-hand side of your regression, and one of your x's is squared, right? And so the slope ends up being a more complicated function here. And that relationship ends up looking like this, which in my case, with the curve, so the 1 day of appreciation would be the flat part, and then consecutive days of appreciation or depreciation, of course, would take you down either leg. Now, then he has a really nice summary on on table 7.1 of, look, just so you don't have to go look back through the chapter, that's what it would look like, and when this changes, the change in y when x changes is what? Really nice. He does a really good job of these summary things everywhere. The next concept in this chapter is lagged independent variables. And sometimes you're going to have a variable that is, first of all, let me write this up here, very common. The stuff I've been showing you here, there's a number of different lags built into that. Y sub t is equal to beta sub 0 plus beta sub 1. What does he got here? Yeah, all right. X sub t minus 1. It could be that the impact, let me finish this off. It could be that the impact of x doesn't show up for another month, whatever our time period is, if it's months, if it's quarters, whatever, it may not show up for a while. For example, going back to this was a study of investment. Well, the thing is, the firm makes the investment decision that they act on in January, well before January. So they make the investment decision for January months beforehand based on data months beforehand. So my investment decision is really being affected by economic circumstances that exist before that. And so it's a very common thing in time series to have, and that was something I really struggled with in trying to figure this out. I struggled with on the theoretical end, especially because it's not always going to be the same lag. So you're sort of shooting for sort of an average lag here. Some firms may, break ground very quickly after they make a decision. Some firms, it may be, a half a year before they act on their data. And so, you're shooting for sort of an average there. And that's one of those places where you could play around a bit with the lags. I decided not to in this paper. I found some theoretical support for the particular lags I had. And I was worried that I invented these FOR and SUR variables here, and so I felt like I was already opening myself up for criticism. It's like, well, you just made those up to where they would work. So if I had then also tried 10 different time lags and so forth, but like, well, you just picked the one that worked, which I didn't. I made up one based on the theory, and it worked, and so I stopped then. There will be lagged independent variables. The last concept, and in keeping with my half an hour here, I may need to stop and start. This will be a very short second video, but it's a really neat concept. It's slope dummy variables. So let me stop and start again.